So good morning, everyone. I was invited to present as a Gustavo Colonnetti medalist, and I would like to say that I'm very grateful to the committee and to Rilem for this prize. So I have chosen to present on magnesium in cementitious material because this is what I started to study when I did my PhD, and I think it's quite a nice topic. It's also a quite broad topic, so I will also try to explain a bit the scientific approach behind. But first, the advance in magnesium in cement chemistry would not have happened without the work of my former supervisor and collaborator. So I would like to thank them very much. And obviously, without them, I would not be here today. So first question, why do we look at magnesium in cementitious material when we know that magnesium oxide is only a few % in Portland cement and that it's precipitating as hydrotalcite? Actually, magnesium content in cementitious material is forecast to increase, and particularly with the use of SEM. And we will use more and more SEM to reduce the amount of Portland cement and more generally to reduce the CO2 in the construction. So here I have taken the example of slag. It's almost outdated, but it's quite a concrete example because it contains a non-negligible amount of magnesium. So here you can see we have the Portland cement, as I said, with a bit of magnesium oxide, which is a model to precipitate as hydrotalcite. And then when we increase the magnesium content, when we increase the slag content, you can see that the magnesium is modeled to precipitate as hydrotalcite. But this phase is not really crystalline. It has a variable composition, and it's quite difficult to observe experimentally and particularly to quantify it. Also, in the purpose of giving alternative to calcium-based cement, there is some teams working on the development of magnesium-based cement. It can be magnesium silicate cement or magnesium carbonate cement. Here, I don't want to give too much detail, but just in both cases, we have magnesium phases precipitating, and they are nanocrystalline. So here I have put the XRD of those two types of cements, and you can see that we don't have like clear reflection peak, meaning that we have nanocrystalline phases formed. So it can be magnesium silicate hydride, so M-S-H in the case of magnesium silicate cement, or it can be magnesium carbonate cement phases. On the magnesium carbonate phases, I will not explain too much anyway. Another point is that magnesium is observed to precipitate at the surface of concrete in contact with saline water, so seawater in that case. So it can be either brucite at the surface or the formation of MSH within the first centimeter of the concrete. And it quite interestingly, in environment where magnesium concentration are quite low, as in groundwater or in river water, you can see also a magnesium enrichment at the surface of concrete. And the study of this nature, of this phase, of this magnesium phase, is quite difficult because, as I said before, it's quite nanocrystalline or semi-amorphous phases, and it's also small amount precipitated. And finally, just a slightly different environment in the context of clay cement interface. There is a presence of aluminium, and there is also some question about if we precipitate hydrotalcite or MSH. On that example, I don't want to give too much detail. It will be actually a case study I will present later. Okay. So to summarize, we have a small content of magnesium precipitating in calcium-based cement, or we have lots of magnesium-based phases when we are talking about alternative binders. But in both cases, magnesium phases are nanocrystalline or semi-amorphous, present variable composition, and it's quite difficult to study in complex matrices. So this is why we worked with simple systems. So this is batch experiment, or we can also work in simple system as cell. I will show you an example later. And working with simple system, simplified system, allows us to synthesize what we want to isolate, the phase we want to isolate, and we can look at the structure, and we can also understand the range of composition of those phases. At the same time, when we analyze a solution at equilibrium with a solid, we can adapt and produce new thermodynamic data to implement the database and to improve the modeling. And working with a simple system then helps in the understanding of real system as durability studies, but also for the development of new material. So it can be for the characterization, because then when we know the structure and what we are looking for, then it's maybe easier to find it. And also we can, with the thermodynamic data, we can then look at the modeling. We'll come back to this model later, and we can also kind of predict what will happen when we are working with development of new materials. And the goal of simplified system is basically to understand the real system, and then we need to have some question, some unknown answers. I mean, yeah, we have some question. We need to find some question to be able to feed the work in laboratories. So I will start this presentation with a study I was part when I was at University of Bern. So it's an interface between claystone and concrete. And I chose to study this degradation because, yeah, I think this is a good example to highlight why we need to work with simplified system. In the second part, I would like to give some updates on a simple system I deeply studied. So it's a magnesium silicate hydride, and particularly the formation of this base, and also give some detail on its structure because it's quite different from CSH. And finally, in the third part, we will look at the stability of magnesium aluminum silicate system, and specifically the stability between M-S-H and hydrotalcite, both with experiment and modeling in the context of development of new binders. So this is an example, a real example, but quite complex system. So it's a 10 years old interface between, at the left, the opalinous clay. So this is a claystone containing 50 to 60% of clays, and Portland cement. And this was in contact during 10 years. And this study was made in the context of safety of repository for nuclear waste. So if we look at the chemistry by EDX, you can see some classical profile. We have the decalcification, so here the concrete and here the clay. And you can see that we have a decalcification close to the interface. We have also enrichment of silicon and aluminum. Then we have some enrichment of magnesium and sulfate. Actually, we have a higher enrichment of magnesium in the clays here, but this I will come back later on that. And then you can see that we have the enrichment of chloride and sodium as well. So here I have just summarized the different changes we observed previously. But the point is the chemistry doesn't give too much information on the mineral changes. So we actually look at the mineralogy, and we carried out XRD mapping. So this was made at a synchrotron facility where you see we have some maps of Portlandite superimposed on the map of calcium, and this is sulfate in that case. So we have maps, we obtained maps for Portlandite, for CSH, even if it's nanocrystalline, we had enough CSH in the matrix to be able to see it, and also maps for ethangite. And you can see that I think it's well known, but somehow it's also nice to see it like by XRD and by mapping. It's like we have this dissolution of Portlandite at the interface. And in that case, you can see that the intensity of CSH and also from ethangite decreased. So this confirmed that we have dissolution of the calcium base phases, and we had the release of the calcium and the hydroxide group into the clays. And this migration and this pH actually induced a dissolution of the clays, and we had the release of magnesium, sodium, silicon, and aluminum. So here we have a sketch including the mineralogy change, and the situation is quite well explained for calcium. And this is actually a result of 10 years work in the context of a repository. But you can see that we didn't, by this technique, with this XRD mapping technique, we were not able to solve, we didn't see any specific feature when we had those enrichment. And this is due to the fact that we have not so much of those phases was precipitating, and there's still open question as what's happening with the precipitation of magnesium. Also, do we have precipitation of some precursors at the interface, and which phases the uptake of sulfate and chloride will occur. And those difficulties come from the amount, as I said, we don't have so much phase precipitated, and we have also presence of other phase, particularly here we have the presence of clays. It's quite difficult to understand, especially here the magnesium precipitation is in the clays, but then usually for seawater we have the precipitation of magnesium where we have decalcification. So this might include more transport that's at the concrete in seawater. So just to understand maybe the same phenomenon, but then we went back to simple system to really understand what's happening in the field. Because meaning when we worked with laboratory scale, it's quite easier, we don't have the dilution effect and we can really focus on the problem. So this is what I will start with a study of M-S-H. So this is what I did during my PhD. So we worked in batch experiment, meaning that we add magnesium and silica fume into water, and after a few years we looked at the solid phase and the liquid phase to answer to the question about what's actually M-S-H. So M-S-H has been related to hydrated phyllosilicate with a TOT or TO structure. So it's corresponding to silicate layers, so like in clay minerals. And a very nice way to observe M-S-H is to use silicon enema. So where the silicate layer can be observed when we observe Q3. So just a short reminder, we use the notation Q0 to Q4 to describe the silicate network. So basically Q1 would be a silicate with one neighbor, Q2 would be a silicate with two neighbors, and Q3 would be a middle of a layer. And this Q3, so the layers of silicates, is really different from the CSH. Here I have put some structure, and also simplified structure. You can see that we have either chains of dimass when we are talking about CSH, and we have mainly Q2 or Q1. So you see we have really different structures, so different phases. Now, if we focus on the M-S-H, we have also quite a lot of Q2 in the structure, and this has been associated to very short layers. So very small particles, and also if we go back to any XRD of M-S-H, we have those broad hump, and you can see that it's not really crystalline. I mean, it's known as crystalline, nanocrystalline phases. Now, if we look at the content of water, there is some thermogravimetric analysis. We can see that there is two types of water, the bond water lost below 200 degrees, and the hydroxyl group. So the bond water would be absorbed, and then we have the hydroxyl group on the particles and in the structure. And this water loss hydroxyl group is quite high compared to CSH. This is something I wanted to say. And yeah, we have a lot of hydroxyl group, and also when we look at some cation exchange capacity that we have measured. So this is cation exchange capacity is actually something we do for clays, and we observed that we had also a negative surface, usually as in clays, and that's at the opposite of clays. When we increase the pH, we have actually a higher cation exchange capacity, meaning that we just deprotonate the hydroxyl group, and we have even more cations coming to compensate the surface. So I would like to conclude this part by saying that M-S-H is much more related to clays than to CSH. Okay, now I would like to focus on the formation of M-S-H from CSH. Why? Because we wanted to reproduce the field experiment with the calcium, the CSH decalcification, and the observation of magnesium enrichment. So I have put the disk of CSH together with the disk of M-S-H. And after 3 months and 12 months, we looked at the solid and the liquid phase. So when looking at the CSH side, you can see that we have decalcification associated to cracks. So here I have put it like, I think we see even better with this gradient pointing to the M-S-H phase. Something I didn't show here, it's like by infrared, we could see that we had 2 types of silicates. So we have the chains characteristic of the CSH when we looked deeper into the CSH disk, and we saw the layers of M-S-H at the surface. So this indicated that we had first destabilization of the CSH and then the formation of M-S-H. But there is no replacement of magnesium in the CSH structure. So just a few words here. When we look at the M-S-H side, because it's really different, we had an homogeneous disk. It was basically, M-S-H was not destabilized. We had few big spots of calcium. We suppose it was precipitation of calcite. Even if we wanted, we tried to avoid this. But the interesting part is that all over the disk, we had some calcium, a small calcium enrichment. And this actually indicated also by other techniques. I didn't show it here, but like we saw that this calcium is actually compensating the negative surface charge of the M-S-H. So the calcium was at the CEC sites. So now I would like to move on to the next part, which is the incorporation of aluminium in magnesium silicate hydrate. So for that, we have worked in that experiment, again, working with magnesium oxide, silica fume, and metakaolin. And we look at the solid, and the aluminium NMR indicated that we had 2 different sites. So aluminium 4, which is characteristic of the incorporation of aluminium in the silicate layer, and one octahedral layer, aluminium in aluminium 6, which is characteristic of the octahedral layer. And we look at the XRD and TGA, and we couldn't observe any aluminium hydroxide or any hydrotalcite. So we suggested that actually this aluminium 6 was incorporated in the magnesium octahedral layer. We also performed TDM-EDX, and we observed also a layered structure consistent with this layered morphology that we can see for pure M-S-H. So here we kind of observed a new phase, which is a magnesium aluminate silicate hydride. It's really similar to M-S-H. It contains small amount of aluminium. And for this phase, we suggested very simple thermodynamic data. But clearly, a lot of work is still missing on that topic, because here, for example, we worked with very simple system. But then when we add a bit of sodium nitrate and we try to control the pH a bit lower, you can see that we actually observe the presence of hydrotalcite and even a bit of aluminum hydroxide. So in that case, we were not really sure if aluminum was incorporated in M-S-H. So there's still a lot of open question as how much aluminum can be incorporated in M-S-H, and also what type of anion can be incorporated in hydrotalcite. Because here we were working with sodium nitrate, so maybe nitrate went into the structure of the hydrotalcite, and also what are the effects of the different anion incorporated in hydrotalcite on the stability. So a lot of questions. So just to try to answer some of them, at least on the stability of hydrotalcite, I went back to work with simple system, and I did some synthesis on hydrotalcite containing carbonate, sulfates, chloride, and nitrate. And we produced some thermodynamic data, including solubility product, heat capacity, entropy for the different hydrotalcite formed. And we made a very simple solid solution, but at least we have some data where we can incorporate those anions into the modeling. And now if we go back to the open question that we had from part 1, you can see that when we do some modeling, so we have the MASH phases and the hydrotalcite phases, you can see that most likely the magnesium phases we have included now in the system will precipitate. Okay, maybe I should explain. Here we have like the pure cement paste, and then we just add more in this modeling. We just add more and more clay post solution. And when we see that when we have a lot of clay post solution, you can see that then we are precipitating those MASH phases and hydrotalcite phases. But in that case, when we go back to the system, you can see that actually magnesium phases are actually precipitating the other side. So now we would need to conduct some transport experiment with those new data to be able to continue to work on this, on solving this those questions. And also here we didn't touch at all about the NASH phases we could precipitate at the interface. So now a final point I would like to talk about is about the development of magnesium-based cement, and specifically the magnesium silicate cement, because it seems more relevant to use calcined clay as a source of silicate, but then it's involved a non-negligible amount of aluminate. And somehow we can model those phases. We can model what phase can precipitate by thermodynamic modeling. But actually, experimentally, we don't always observe those phases. So there's plenty to understand, especially when we see such difference in compressive strength by replacing silica fume by metakaolin. So here it was an example where I used sodium carbonate as an additive to accelerate the formation of a message. And I didn't work with very low water to cement ratio, so obviously we have not so good mechanical properties. But then there's other teams where working with low water to cement binder, and you can see that they reach very high compressive strengths. So there is really a lot to understand of why we have such difference when we use metakaolin instead of silica fume. So now to conclude this presentation, I have presented few experiments in simplified systems. So first, I hope I convince you that M-S-H is more related to a clay than to a CSH and can incorporate also aluminium. And in second part, we looked at the degradation of cementitious, calcium-based cementitious material. So dissolution and destabilization of the CSH, and then the precipitation of M-S-H. Also, we developed some simple thermodynamic data for magnesium phases to help in the understanding of degradation of concrete. But obviously, more work has to be done, in particular for this example where we see that we need transports. And finally, M-S-H is a cementitious phase. It can show some mechanical properties. They are not too bad, and it's even improved when we have aluminium in the system. But there is lack of understanding why, and somehow there is plenty to investigate in the future. Okay, to conclude this talk, I would like to say that I do believe that there is a future for magnesium-based cement, especially when we see how MASH phase can look like clay minerals. Thank you for listening to me. I hope this presentation gave you some insight on magnesium phases, and I will be happy to answer to your question. Thank you.